Well, one thing that seems to be bothering some people in class is the fact that we've got these constants of integration, and doesn't the shaft just go where it's supposed to go whether we define the constants or not? And so I thought the best way to illustrate that is just show you a couple of lines here. First of all, we have a dashed horizontal line, and let's think of that as the x-axis for right now. That represents the rest state or the neutral axis of the shaft, so y equals 0. We have a thick kind of squiggly black curve above that, and let's say that that curve represents the y function. If we think of it in singularity terms, that is the shape of the shaft after the loads have been applied. And so that thick black line is the deflection of the shaft. But it's not necessarily true that it's going to look like that when everything is said and done. All we can say about that, the deflection of the shaft, is that the general overall shape is going to be that. And so the reason those constants come into play is, I'll just grab this. The shape of the deflected shaft has what we would call 2 degrees of freedom. For every point on the shaft, wherever we are, it can have a position, a y position, essentially its distance from the x-axis, but it can also have a rotation. Another way of saying it is any 2 points on this shaft can be defined in terms of their y deflection, and that pins it in place. Let me try to make it a little bit more clear. The way it is right now, the shape of that shaft is set, but it can be anywhere. There's an infinite number of possibilities about whether it's above or below the x-axis, but even more than that, there are an infinite number of possibilities about its rotated angle with respect to the x-axis. So the curve keeps the shape, but it can be really any angle of rotation that you can imagine. And so we have an infinite set of possibilities. There are all sorts of different configurations that we can have that represent the true deflection and angular deflection of the shaft at any point. And so we need to specify something. And in the case of the problem in class, we really only had one thing that was absolutely specified at first, and that was the deflection of the shaft at bearing D. And so let's say that roughly this area is where bearing D is. We said that its deflection was 0. So that fixes point D. Its y value corresponds to the x-axis, it's 0. And so now we have still an infinite number of solutions, because this shaft, even though it's centered at 0 there, or it's 0 at bearing D, it could have any angle of rotation that we can imagine. And so that's why we have to apply a second constraint in order to determine exactly what the deflection of the shaft is at any point. There's 2 ways that we can do that. We could define the exact y value of some other point on the deflected shaft and essentially pin it somewhere. So that could be the x-axis, that could be 0, or that can be some finite value. However, what we're doing in this problem is we're defining the angle of the shaft at the bearings. So first of all, we're saying that there's a maximum allowable angle, slope, or angular deflection, however you want to say it, of the shaft at bearing D, but also if we come over to the other side of the shaft, if bearing E is over here, there's a maximum allowable angle there. And because of that, that now fixes everything that we have, and it tells us exactly what the deflection of the shaft is. I'll bring your attention back to what we would have done early on with deflection and stiffness when we talked about an ideal wall. In that case, the deflection at the left end of the shaft is 0, so we pin it to 0 there, and at the same time, I'll see if I can manage this here, we have an angular deflection of 0 at the wall as well. So let me try to get that angular deflection to be what looks like 0. And let me move it down. And so there you go. With these same loadings, if that were a thrust bearing at the left-hand side, or if it were an ideal wall instead of a thrust bearing, that's what the deflection of the shaft would look like. In that case, just about all the deflection would be negative. But you realize the shape of the deflection hasn't changed. It's just the up and down or y offset of the deflection and the rotation of the deflection about the origin.